How's it going? I'm John.
Gabe, nice to see you.
And we are here to talk to you about how you probably don't need neural networks. Maybe some of you do, but most of you probably do not. Many simpler algorithms can solve your problems with less headache.
It's going to be a very opinionated talk, so feel free to heckle as much as you'd like. Should we talk about ourselves a little bit?
Sure.
What we do? Or we do that later?
Let's start now.
Okay, we're doing that now. You want to go first?
We used to work together at a company called Magnetic, which is now called Deloitte Digital. You might notice this from your bands. I currently manage the machine learning team at OkCupid.
I work at a company called United Technologies. It's an aerospace manufacturer. I manage a data engineering team there.
Let's get into it. So neural networks get a lot of hype these days. And for many applications, they're definitely what you want, sound, vision, text especially. For other problems that many of you might have, models that require fewer architectural decisions and hyperparameter tuning can often do just as well. Plus, GPUs cost money. You probably don't have them on your laptop. And in general, my general viewpoint is that most machine learning models will get the job done for most of your problems. And really, for most machine learning problems that are, full stack, which model you use is kind of the least interesting and impactful decision you're going to make. With that being said, we're going to talk a lot about that decision today. So,
right on. Yeah, just to jump on the GPU a bit, a lot of the work that we do at United Technologies is a lot of on-prem processing, and so GPUs are certainly a scarce commodity at times. Sometimes hard to get that as a resource. So I think that initially when you're encountered with a problem, I normally jump at, okay, let's just use some deep learning algorithm, but that's not always the right path, I would say.
Yeah.
Yeah.
Let's get into it. So we're going to talk about a few types of models. Our core assumption is that many of you might have an understanding of what machine learning is, but not know what every model is about. We'll talk about the trade-offs involved between these models. We're going to test each of these models on basically 3 benchmark data sets and talk about what these results mean. So one of them is called logistic regression. I suspect most of you all know what regression is. This is a lot like that, except the number it outputs looks and acts like a probability. And so if P is a probability that some event you care about is going to happen, what this looks like is this weird function of P on the left side is equal to the intercept plus a weighted average of various features. Sorry, not weighted average, a weighted sum of various features. Those of you from statistical backgrounds call weights coefficients. It means exactly the same thing. This fancy part of the left is not something we're going to get into, but that's the part that makes it logistic regression, not regression. Makes it look like a probability. And this is simple. It's easy. But to make it work for many non-trivial problems, you need a lot of feature engineering. And feature engineering means that you take your data and you add on other functions of the data.
Is it obviously a data scientist? Does it always have to be a sigmoid? What is a sigmoid?
What is a sigmoid? To answer your first question, some people use a probit there, which is another function that is kind of the same thing. Let's not get into.
Okay. No,
we have some banter planned, but
That was the wrong banter. Sorry.
A neural network is the simplest way. It's a generalization of regression, and multi-layered neural networks means you're doing regression on top of regression. So what that looks like is, here's a very simple example of a feed-forward neural network. Feed-forward means it goes in one direction. It doesn't go in circles. Raw data input layer is a fancy term for your input data. Output layer means this is your output. And if all these arrows are intimidating, just understand that each of these things are called nodes or neurons or units, and each of them is just a result of a regression and then an input to another regression. So it looks complicated, but it's actually pretty simple.
Back in my day, we called them perceptrons.
Oh, yeah. Worth pointing out that some people call neural network like this a multi-layer perceptron, which kind of just means it consists of simple layers stacked on top of each other. There's no convolutions or loops. The point is that there are many different neural network architectures you could try. I listed as many as I could to make it look really intimidating and make you understand that neural networks involve lots of decisions. The spoiler is neural networks involve lots of decisions that you can just punt on if you use other methods. Gradient boosted trees are a algorithm I've got a lot of love for. You take a decision tree and you keep on adding more decision trees to correct mistakes the previous ones made. So if you don't know what a decision tree, it's kind of just a series of if-else statements. In machine learning, which if-else statements you make and where they lead you is a learned thing. In this case, it'd be, should I walk or take the bus? And that's a function of how far are you going, the weather, are you hungry, et cetera. And in order to, we kind of went back and forth on how to explain gradient boosted trees, and we ended up writing some Python pseudocode. And so to walk through this a little bit, you start with one tree on your data, and then you iteratively get the predictions using all the trees you've used up until that point. You find the gradient, and to keep it simple, gradient is a whole lot like the error. How wrong are you so far? It's not exactly that, but it's pretty damn close. You fit a new tree to that gradient, to that error. You add it on, and you continue. To get a little bit deeper, I wrote this predict GBT function right there. Start off with your predictions at its base are just the mean value of the output data set. Keep on wanting to, someone in the audience knows that everything I'm saying is approximately wrong, but that's okay. I'm sure many of y'all know it's approximately wrong. Anyway, you start with the baseline, and you add a weighted sum of your trees, with the weight being this thing we call learning rate. Good?
I think that makes sense.
All right. Yeah, so we talk about trade-offs. This is the part where even more caveats exist. These three you talked about, they require different levels of feature engineering. So neural networks, a complicated one can do all the feature engineering you could ever want, but maybe it can benefit from some feature engineering, but it's not really necessary. Logistic regression desperately needs it, and gradient boosted trees falls somewhere in the middle. This is why neural networks work for vision tasks, and I once took a class in grad school about machine learning without neural networks, and well, just if you ever want a good time, look into what that involved, because it was pretty scary. In terms of how much you have to think about the architecture, gradient boosted trees and logistic regression are relatively out the box. They have hyperparameters, but in my personal experience, the outcome tends not to be super sensitive to what they are, given reasonable defaults. Neural networks, it's all iteration and hyperparameters, which is not a kill. It doesn't mean you should never do it, but it's an issue. Training time, neural networks obviously can vary a lot. But logistic regression is super fast and simple, and gradient boosted trees is usually non-trivial. I'm not getting heckled yet.
That's good.
They might be asleep.
So wait, it looks like the GBTs take a long time to train.
Yeah, and we have some output data, some results from our training to show y'all.
So even though they take a long time to train, we're still rooting for them, right?
I think I have an irrational love of them.
Okay.
But they are great. I should also point out gradient boosted trees, you'll see them gradient boosted classification trees, gradient boosted decision trees. I want to keep it simple, but they're basically the same thing. Gradient boosted regression trees means you're outputting a linear value instead of a 1-0 or classification. That's the big difference. There's also deployment architecture. So I recently, for something we were doing at OkCupid, one of the teams wanted me to do something that I did not want to have to worry about deployment and new dependencies in their workflow. So I built a logistic regression model. I put the coefficients into a JSON file. And it's here, it's get tracked. You can build a system that downloads that JSON file and uses it. It's simple. Whereas gradient boosted trees and neural networks, generally speaking, are going to have to install something new for production dependencies. Yeah. to talk about some data sets.
So yeah, we wanted to benchmark some of the different algorithms on essentially two different data sets, the Higgs data set and the MNIST, which I think everybody knows. Higgs is a generated data set that's, oh man, what is this one? This one is, it's a kind of rather large data set.
Big.
That has essentially 21 to 28 different features to predict whether or not it's a positive, generating a Higgs particle, essentially. I mean, there were 2 talks ago, there was a physicist that was talking.
We really should have made this a 3-way talk with
yeah,
physicists.
kept the caller back. So I don't really know that much about that, but large data set to crunch through, and it was a good one to play with to benchmark what we were doing.
Yeah, the reason this data set was compiled for the express purpose of testing whether the 7 engineered functions of the first 21 features are actually necessary if you have a complicated enough model. So this is why we use this for our benchmarking.
And of course, MNIST, someone described it as
Classic.
the hello world of machine learning. It's handwritten numbers, essentially. I learned that it was high school students and U.S. Census Bureau taken from their handwriting, which is somehow interesting to me, and normalized to be same size and very easy to use.
What if anybody's built a model to predict whether there's a high school or a Census Bureau?
That would be. We can do that next year.
Right. So we basically threw all these models well, not all the models at all the data sets, but pretty close. You'll notice we did 5 runs each, so some of them kind of overlap. But this is Higgs raw, which you might remember means it uses these 21 properties that are truly measurable things and not the 7 engineered features that physicists came up with. Spoilers. And so first off, okay, let's back up. Machine learning people tend to hate putting slides with accuracy on it because it depends, most data sets you deal with, it's 92% no, and therefore you can get 92% accuracy easily. This 50-50, and accuracy is super explainable, so we went with it. Yeah, so logistic regression does better than 50%. Neural networks, whether 1 or 2 hidden layers, do reasonable, and gradient boosting trees do just as well if you ignore the fact that it takes, 8 times as long to train?
Yep.
But hey, this is,
It's
physics is important.
Run it overnight, go to
Yeah.
sleep, wake up the next day. That's what we did.
That's fine. If you added the engineered features, what's interesting to me is you'll notice here, just from eyeballing it, gradient boosted trees and 2 hidden layer neural network does basically just as well on the raw data. But when you give it the boost of the engineered features, everything does better, but gradient boosted trees with that extra boost just rockets its way up. Yeah, and logistic regression also gets a bump, but not, it's still lagging behind, which is what expected. Finally, on MNIST, we just used 2 convolutional neural networks, which we didn't bother telling you what convolutional meant, but it's basically how neural networks are used for vision and gradient boosting. That's 98% or something like that?
Yep.
So this data set, if you were guessing randomly, you get 10% accuracy because the numbers are distributed randomly. That's extremely good. Gradient boosting, I'm always surprised. I've thrown it at a few image data sets just for fun. I'm always surprised at how well it does. It's one of those things that just shouldn't work.
Right.
And it does because it's magical. Although, of course, 8 times training time. But
So you would say that you would use it for image classification.
you could. I mean, if I don't know, if you were literally allergic to neural networks, you could. But come on, 98%.
It's pretty good.
Yeah. Yeah, so that's most of what we have to say. Neural networks can do feature engineering. When you already have feature engineering done already, other models can usually do about as well. And neural networks are great at vision. All of our code is on the GitHub.
The GitHub.
The GitHub. Also, it's Gabe's birthday.
Thank you.
Yeah. And
Not enough candles on there.
should have been a better image. And it's worth pointing out that while we work at 2 separate companies, you can't really have a presentation without telling everybody that we're hiring.
That are not merging. United Cupid Technologies.
Not yet.
Okay, yeah.
Yeah. And that's everything, unless y'all have questions.
Nope.
So the first hand was there.
What do you do when you have a really, really noisy data set?
Really, really noisy data set. That's a broad, I mean, like, it's a broad question. You're gonna, I mean, so.
What's your gut instinct? Where are you gonna start? Where are you not gonna go?
So on the subject of neural networks versus not neural networks, one thing that someone told me once that I thought was very insightful was that neural networks are built for problems that are not noisy, but like the structure of whatever you care about inside this highly multidimensional space is weird. So if you're trying to separate cats and dogs, like the actual pictures are can be crystal clear. There's not like someone's adding random noise to these dogs and cats. It's just that what is a dog and what is a cat are complicated things that a neural network can figure out. Whereas basically every other, most other machine learning algorithms are built for a world, which is what you're talking about, which is like there's a relatively simple, what word am I looking for? Structure of what separates, if we live in binary classification world, what separates the yeses from the nos is just there's noise added onto it. I don't think I'm answering your question at all.
If you notice, we used prepared data sets for this one.
Yeah, but noise is a very real world thing, and I mean, I used to work in online advertising, and in a sense I still do, where okay, online advertising in particular, like people buying whatever you're advertising to them is a very rare event, which is very little of it is like what's in your ad, and much more of it is like how they're feeling that day. So we used logistic regression with feature engineering, and it worked pretty well.
How much love do you have for XGBoost?
This was XGBoost. We didn't try any of the other gradient boost
We
libraries.
did. We tried with the TensorFlow one, I think.
Oh yeah.
For like a hot second.
Yeah.
Just because it was easy, and then that was a bad idea.
Yeah, anecdotally, another Google people here, but anecdotally I've heard TensorFlow gradient boosting is not great, but there's like 5 other libraries with that people seem to like. Microsoft has one, Yandex has one. Yeah.
So, I mean, it just doesn't need GPUs to train, but it still takes longer. This is why is that? Does it really work out?
So in any application you have, there's some places you're like, I don't care if it takes 3 hours versus 10 minutes. And some applications you're like, yes, I care a lot, and I think that is got to drive your decision. All right, I think we questioned them out.
Great, thanks.
Thanks, everybody.